Okay, today we're going to begin the last case for integration using partial fractions. This is the case where the denominator has a quadratic factor. For a quadratic factor, which will be of the form ax squared plus bx plus c, we will have a fraction of this form. Notice the numerator no longer contains a single letter, but rather the numerator is linear. Okay, so let's look at a first example. The first thing we do with these examples is ensure that the denominator is factored. In this case, there is a common factor of x, which we remove like this. The numerator, of course, is going to stay the same. So now, if we take a look at that denominator, we would consider this to be a linear factor and this to be our quadratic factor. Notice that this cannot be factored. There's no such thing as sum of squares factoring, only difference of squares factoring. And that means in order to integrate this, we are going to have a denominator of x and a denominator of x squared plus 4. Two separate fractions. This first term has a linear denominator, and therefore a single letter will be included here. But this is a quadratic denominator. So up top we need this, bx plus c. Now, if we were going to add these fractions together, of course we would need to move to this common denominator here. This means that a would be multiplied by x squared plus 4, and the binomial bx plus c would need to be multiplied by x. So from this, we get our main equation. Take that original numerator and set it equal to this new numerator. Like that. And you'll now notice that what we need to do here is solve for three unknowns, a and b and c. Of course, we've learned the skills for doing this. First, we substitute any roots that we might have. We have here the root x equals 0 to work with, so we start with that. If we substitute 0 on the left, we will have 4. On the right, we're going to have a times 4 plus bx, it's b times 0 plus c times 0, actually. And the point is the 0 here would eliminate this entire term. Okay? So yes, we would be substituting 0 here and 0 here. Okay, but the 0 here wipes out that whole term. From which we have this. 4a is 4, and now we know the value of a is 1. All right, now we need to figure out values for b and c also. We are all out of roots, and it is too early to substitute an arbitrary number. We need to use the coefficient method, and often it works to start with the highest power, which is x squared in this case. On the left, we have 5x squared. On the right, where do we have those like terms? Here, ax squared And notice here is also bx squared if this bracket were opened up. So we have 5x squared is equal to ax squared plus bx squared, from which 5 is a plus b, and since a is 1, we now know b is 4. Now that we have 2 out of the 3 unknowns determined, we can substitute an arbitrary value for x here if we like. Or if we're enjoying the coefficient method, we could do another coefficient. For example, I could do here the coefficient of x. What is the coefficient of x on the left? Well, it's absent, that term, so it must be 0x. And where would we have x terms on the right? Not here, that's a square. Not here, that's a constant. Not here, that's a square. Only here, cx. From which we find that c is 0. Okay, but as I say, you could have also determined that c was 0 if you had substituted an arbitrary value for x at this point, right after figuring out b. The only thing you couldn't substitute, of course, was 0. So you could have substituted, for example, x equals 1. All right, so now we take our values and we substitute them into our partial fractions. So they now look like this. We're going to have 1 over x. And on top here will be 4x over x squared plus 4, like this. Okay, because of course it's 4x plus 0. And now we integrate each of these. I hope you recognize here that both are logarithmic. This one should be quite obviously ln x. And this one has that required exponent of 1 in the denominator. The derivative of the denominator is 2x, and we have double that here. So we actually have this. Okay, we have 1 over x plus 2 times 2x over x squared plus 4, which means we have the ln of x plus 2 times the ln of x squared plus 4. Okay, plus c, yes, but in fact this is a definite integral here. I can combine these logarithms. That would require first moving this coefficient, then having a product for the argument. Okay, so x times the square of x squared plus 4. And then what we would do, of course, is substitute 4 first. So you would be doing here 4 times the square of 20. Okay, and that would give you 1600. And then minus substitution of 1. So it's the ln of 1 times the square of 5. And this you can put into your calculator directly if you like, or in fact you could change it to the ln of 1600 over 25. But either punching this into your calculator or this into your calculator will give you roughly 4.16. Okay, if you wanted to evaluate this integral using a u substitution, Of course, you could do that as well off to the side here somewhere, right? So if you wanted to take this integral like this, then you would be doing, you know, u is x squared plus 4, du is 2x dx. And so this integral then becomes 2 times the integral of 1 over u du, or 2 times the integral of du over u. And that from that it would be 2 ln u. Okay, so I'm going to just maybe put a little box around that to keep it separate from what we did here. Okay, so the key, what is the new bit? After you finish factoring, you are stuck with a quadratic factor. So that means up top, we don't have a single letter, but we have something linear. And that is directed by our formula sheet here, okay? Something linear over top of any quadratic factor. All right, I'm going to go ahead and do a second example with you right away. So here is a second problem. Notice this trinomial is not factorable. We would need a product of 2 and a sum of 2, which is impossible. So we're stuck with this quadratic factor. This is considered to be the linear factor x repeated. So hopefully you remember how to handle that. For just this factor, we need 2 fractions, one with the denominator of x, a second with the denominator of x squared. So in total, for this problem, we need 3 partial fractions. For these 2 terms, a single letter is appropriate. Again, that is a repeated linear factor. For this quadratic factor, we need something of this form, cx plus d. I've already used up the a and b, which is why we start with c. But the point is, this is linear here. Next is the step where we go to the common denominator. So the common denominator, of course, will be this original one. So let's see what adjustments we would have to make to these numerators. A. Currently, under the a is only an x. So I would need to multiply by 1 more x and by this trinomial if I were moving to this common denominator, plus b. Currently under the b is x squared. So what is missing is just the trinomial. Okay, plus now we are here. Bracket it because it's a binomial. Under it is only the trinomial. So what is missing? X squared. So we multiply by x squared. From this, we get our major equation. I have to set this numerator equal to this one. I'm going to write rather small here so that I can fit this in one line. All right, I think I've got it there. Okay, so the original numerator is set equal to this numerator here in this fashion. Now, taking a look at our denominators, we have just one root. It is 0. So we begin by substituting 0. Now, when you substitute 0 on the left side, you will have 4. On the right side, this whole term will be 0, and this whole term will be 0. The only non-zero term will be here. B will be multiplied by 2. Okay, so we are substituting 0 everywhere there is an x, and this is the result. From this, we find that b is equal to 2, 4 divided by 2. And now we have 3 more unknowns, a and c and d. We need to use the coefficient method at least 2 times. We can use it 3 times, but a minimum of 2 times. If we start with the highest power, which is x cubed, we will run into a problem. Because in the right side, it is ax cubed plus cx cubed. And we don't know a, and we don't know c. We would run into a similar problem if we tried to use x squared right now. Because in the right-hand side, we have ax squared, bx squared, and dx squared. And we don't know a or d. The coefficient of x here will work. On the left side, we have 2x. On the right side, where are our x terms? Here would be 1, 2ax, plus, where else? Here, 2bx. Anywhere else? No, that is a cube, that is a square. So we get this equation. Or 2 is 2a plus 2b. b, however, is 2. So we get 2 is 2a plus 2 times 2, or 4. We would subtract now. 2 minus 4 is negative 2. So 2a is negative 2, from which a is negative 1. Now that we know a, we can go back to the coefficient of x cubed. On the left side, 1x cubed. On the right side, let's identify our cubes right here. Ax cubed plus, where else? Here, cx cubed. From which 1 is a plus c. Since a is negative 1, we find that c is 1 plus 1, or 2. And at this point, if you want to, you can substitute an arbitrary value, perhaps substitution of x equals 1, if you like, or you could use the coefficient method again. I'll use arbitrary, I guess. Let's go ahead and substitute x equals 1. So on the left side, you'd be substituting 1 throughout here, and what you'll get is 10. On the right side, I would have a times 1 times 5 plus b, we're substituting 1, so it's b times 5, plus, in a bracket, c times 1 plus d, and outside is a 1. So we end up with this, but we know values for a, b, and c. Okay, so we're allowed to now substitute a is negative 1. Okay, so this becomes negative 5. Okay, plus b is 2, so 2 times 5 is 10. Plus, and the bracket serves no purpose here any longer, it's just addition. So this is 2, c is 2, plus d. If you want to keep a bracket around it, it makes no difference. But the point is, this is 7. 10 is 7 plus d, from which d is 3. Okay, so that was quite a lot of work in order to figure out those values. And now we're going to substitute those throughout. Okay, so back to our partial fractions. This becomes negative 1 over x plus 2 over x squared plus, now it's cx plus d, so 2x plus 3 over top of this non-factorable trinomial. And now to integrate these things. Logarithm, no problem. Certainly not a logarithm. The exponent is not 1. So in order to integrate this, we have to write it 2 times x to the negative 2. Now what about this one? Is it a logarithm? Well, the exponent down here is 1. What's the derivative of the bottom? 2x plus 2. Oh, we have 2x plus 3. We have 1 more than that. So let's push the 1. Okay, so we split this 2x plus 2 in the top of one of these guys. And the other one in the top here. Okay, 2x plus 2 plus 1 more, 2x plus 3 as required. This is now a beautiful logarithm. What the heck is this one? Well, this is going to be our arctangent formula. What does that mean? We have to complete the square on this guy here. Okay, where am I going to do that? I will just get some more paper. Okay, so for this guy, we have to change the denominator to, oops, I've moved my paper. It's probably not on screen anymore. Okay, there we go. I put it back. We have to change the denominator to x squared plus 2x plus 1 plus 1. So the 2 is written this way. That's because this is now a perfect squared trinomial. So we have x plus 1 all squared plus 1 squared. This is our u and this is our a. Okay, so this third fraction we're going to write with the denominator this way. So I need to continue on a new paper. Make sure this is on screen. Just stand myself up for a second. Okay, yeah, there we go. So back to this. We're going to integrate them all in one step. That's why I keep rewriting these ones, even though they're already set up. Okay, so what we did for this last guy is we changed the look of the denominator so that it looks like this. Okay, and now we'll be using u is x plus 1 and a is 1, and this is our arctangent formula. Okay, so now we can integrate all of these in one step. So what do we get? We get negative ln x. How do we integrate this? We simply add 1 to the exponent. That'll make it negative 1, and then we divide by negative 1 here. Okay, so it'll be negative 2x to the negative 1, which is the same as negative 2 over x. Here's a perfect logarithm. Okay, and then I don't actually have that formula sheet in front of me, but it goes 1 over a, so that's going to be 1 over a. Maybe I can write it for you guys here. 1 over a, arctangent or tangent inverse of u over a. This is what the formula is. So it's 1 over 1 out front, and then arc tangent of u over a. So it'll be x plus 1 over 1 as the argument here. So it just looks like that. Don't forget the exciting conclusion, the constant of integration there. Okay, so this could be a final answer. If this bothers us, we could make it negative 2 over x here as well. Lastly, we can combine these two logarithms. So I'm going to do that in a final step. When we combine them, the one preceded by the plus sign will have its argument in the numerator. The one preceded by the negative sign will have its argument in the denominator. So we're going to have the ln of x squared plus 2x plus 2 over x. This is negative 2 over x. And then finally, the arctangent term at the end. Okay, absolute value signs here perhaps. So this is our final answer for that marathon problem. Okay, it certainly was long. I hope that you understood the steps involved there. Please replay the video as required and slow it down and so on. I'm going to pause here before doing example 3. Otherwise, this video will take all afternoon to upload. Okay, all right, so stay tuned for example 3.